Let us look at this example. In this example, he says, consider the Weston Bridge circuit and resistance temperature table given below. At what temperature the bridge is balanced? Very simple question. At what temperature the bridge is balanced? Look here, this is 100 into 1000 equal to 1000 into RTD. That's how the bridge theory. So now the value which will make the bridge balance is supposed, what I can see here, supposed to be 100. This must be 100 or the closest to 100. Either 100 or the closest to 100. When I look at the values, this is the closest to 100. So this is the one which will make the bridge almost balanced. I cannot say balanced, but almost balanced. Okay, in the next part, he's saying if the supply voltage is 15 volt, calculate the output from the bridge at a temperature of 75 degrees Celsius. So here he is saying something, sorry. He's saying something here that if the temperature is 75 degrees Celsius, this is 75 degrees Celsius. If 75 degrees Celsius, that means the resistance is 130, which means this resistance is equal to 130 ohm. That means the bridge is not balanced now. But he doesn't want to know whether it's balanced or not balanced. He wants to know what is the voltage on the output at that time. This is the idea. We will see it in the next slide anyway. Finally, calculate the voltage at point D and B relative to the ground at a given bridge design. So we want to calculate the voltage at point D and point B. We are going to take each branch separately. This is very simple because each side will be treated as voltage divider. So in the first part, we find that it's 99. It's very clear, very simple. When the temperature is 70 degrees Celsius, the resistance is 130 ohm. So when I calculate VBD, substitute the values, and this is 1,000 over 1000 plus 130 into 15, the input voltage equal to 0.362 volt. Now, if I want to go, so this is the voltage at the output when the bridge is not balanced, when the temperature is 75 degrees Celsius. Let's go to the other part. When I want to calculate VD and VB, we are going to consider the voltage divider for one side and the voltage divider for the other side. What I mean by that, 1000 over 1000 plus 130 into 15 equal to this value. And here, 1000 over 1000 plus 100, that's the other branch, into 15 equal to this value. Of course, when you subtract this value from this value, it will give me the same answer as here. When you make this value minus this value, it's supposed to give me same value as calculated earlier. Another example here, he's saying for the RTD circuit shown in the figure below, calculate the output voltage of the amplifier has a gain of 6.05. RTD resistance is 1320. RTD, this one is 1320 ohm, and the gain of this amplifier is 6.05. So we need to calculate the output voltage. Output voltage is the voltage here, this voltage we need to calculate it at measured temperature. That means there is a temperature measured which make the resistance this much. What will be the output voltage? If you notice, this question is very similar to the previous question, except we are going to use amplifier here to amplify the signal on the output. So we can say here that V out is equal to V out B. V out B means this point, between this point and this point. If you want to calculate it one shot, it's fine. If you want to calculate it step by step, it's going to be fine. If you calculate the voltage between this point and this point, it's exactly same as the previous question. So when you calculate it, it's RTD over R3 plus RTD into 15 minus R2 over R1 plus R2 into 15. That's the voltage divider at each branch. So notice, if you want to see, this is the voltage which applied to this branch to the ground. And if I use other color, the same voltage is applied to this branch. So you can apply voltage divider to this branch this branch and voltage divider to the other branch. That's what you can do. So you subtract them from each other as explained in the equation earlier. When we calculate them, you are going to find that the voltage is 1.03 volt. That's here at this point. Now here. Now if I want to calculate the voltage into the output, it's going to be this volt multiplied into the gain, which equal to this value. So the gain of 6.05 into 1.3 equal to the output voltage, which not given here anyway. It's easy value, you can calculate it. Another example, I think no need to discuss this example because it's similar to the previous example. It's very similar to the previous example. In the application of RTD are more expensive than thermocouple. So we can use it when the temperature range in between -240 to 650. Its accuracy is 0.2% up to 0.5%. It's good linearity and repeatability. So we are going to consider these things when I decide to use RTD. Yes, it's expensive, but it will give me more accurate result because it's linear and its accuracy is high. By the way, its accuracy can go sometimes for higher than this. The accuracy for the RTD, it can go for a value which higher than this. And the beauty, another beauty of it is the repeatability. As we are using it again and again, it's not going to lose its properties. It's going to keep its properties and its characteristics. The dominant type is 100 ohm output resistance. The output resistance is 100 ohm and we know it as a PT100. Here is temperature measurement using thermistor. Means the sensor we are going to use is a thermistor. Thermistor is a semiconductor material. It's made of semiconductor. For that, it's more sensitive to the temperature. You will find its change of temperature, the percentage of change per degree Celsius is 4%. Means 4% of change per degree Celsius in the thermistor. But in RTD, it's only 0.4% per degree Celsius, which shows a great change in the temperature and the resistance as the temperature is changed in the thermistor. The problem of the thermistor, it's having its characteristics highly nonlinear. We will see this in the next slide. Here the characteristics of thermistor is shown, which showing a resistance versus temperature, and it shows the relation highly nonlinear as you see here. Now if I want to consider the sensitivity and compare the sensitivity of thermistor to the sensitivity of RTD. If I consider in both cases 2000 ohm resistance for the sensor, it's found that for the thermistor, there will be, if the temperature is changed by 25 degrees Celsius, there will be a change of 80 ohm per degree Celsius. Unlike the thermistor RTD, in RTD you will find the change of 25 degrees Celsius is 7 ohm per degree Celsius. That means here the change of resistance versus the temperature is going to be very small. Now, if we want to make relation between the resistance and the measured temperature, the relation is to be found from this equation, which the resistance R is equal to R node exponential of beta into 1 over T minus 1 over T node, where R is the resistance for the new temperature, but keep in your mind that the temperature given here in Kelvin, and R node is the temperature at T node. Whatever T node, let's say the room temperature is T node, the resistance at that time is R node. You can proceed with the calculation based on that. Beta is the material specific constant. It's a constant for the material used to make the thermistor. Thermistor type are two types. We have negative temperature coefficient and positive temperature coefficient, where in the negative temperature coefficient you will find as the temperature increase, the resistance will decrease. That's why we call it negative coefficient. But in the positive coefficient, you will find the opposite. As the temperature increase, the resistance is going to increase, as you see here. So for higher temperature, there will be higher resistance, unlike the previous one. So these are the two types of thermistor. Now to use the thermistor, as we know, its output is resistive. So we can convert that resistance to voltage through this kind of circuit. For example, this is one of the circuits to be used to convert the thermistor to thermistor resistance to a voltage. So it's simply we allow current to flow in the resistance of the thermistor. Current will be allowed to flow in the thermistor, and that's going to cause voltage on the output. So the change of the resistance will cause a change into this output, which means the change of temperature, will change the resistance, which will change the output voltage. So the output voltage is calculated as RT into R into I EX. That means the resistance of the thermistor multiplied into the current flowing into the thermistor. If we have a voltage source, not current source like the previous slide, if the voltage or the supply is supplied through voltage source, what we can do here, we can use voltage divider. A voltage divider means R node is to be connected in series with the thermistor. So we can calculate the output voltage as VEX, means the voltage of the supply, the mean voltage of the supply here is VEX, multiplied into RT, which here, divided by RT plus R node, which voltage divider. So again, the previous one is showing the situation if we are supplying the RTD, the thermistor by current source. Here, if we are supplying the thermistor by voltage source, so we need voltage divider. Voltage source here, we need voltage divider to convert the resistance of thermistor to. Let us consider this example on thermistor. The example is saying a 10 kilo ohm NTC thermistor, means negative temperature coefficient thermistor, has beta equal to 3455 between a temperature of 25 degrees Celsius and 100 degrees Celsius. Calculate the resistive value at 25 degrees Celsius and again at 100 degrees Celsius. So what do you mean by this? Let us consider how he produced the data. The data given beta equal to 3455, and at 25 degrees Celsius, the resistance is 10 kilo ohm. At 25 degrees Celsius, the resistance is 10 kilo ohm. Now, when I want to use the temperatures, the equation which we discussed earlier, I mean this equation, accept the temperature in Kelvin. So we need to convert whatever temperature we are going to use from degrees Celsius to Kelvin by adding 273.15. He's saying here the value of R1 already given as 10 kilo ohm. Yes, it's 10 kilo ohm R1. Base resistance. Thus the value of R2 at 100 degrees Celsius is going to be, so R1 is given 10 kilo ohm at 25 degrees Celsius. If I want to calculate 400, what will I do? We are going to use the formula. So the formula is saying R equal to R node. R node means R1, means the voltage, the resistance at certain temperature, which considered as the room temperature. So R node equal to 10,000. As you see here, we put 10 kilo, 10,000, exponential of beta into 1 over T. What do we mean by that? It's beta is the constant into 1 over T, where T is equal to 100, because I'm calculating now the resistance for 100. Plus 273, that's conversion from degrees Celsius to Kelvin, minus 1 over 25, but in Kelvin. So when we substitute or when we calculate, you are going to find that the resistance at 100 degrees Celsius is equal to 973. Notice here that the temperature or the sensor is NTC, as I mentioned, negative temperature coefficient. So when the temperature was At 25 degrees Celsius, the resistance is 100 kilo ohm. And when the temperature 100 degrees Celsius, the resistance is less than 1000 ohms. That's what we mean by negative temperature coefficient. Strain gauge. Strain gauge is the device which use, or the sensor which used to measure sometimes the force or the torsion or the deformation of the material, if I can say. So if I want to define the strain is the amount of deformation of the body due to applied force. What do I mean by this? If we apply force to this bar, the bar will change its length. Its length will change. It's having a length of L node. After that, it will become L node plus delta L plus some quantity. Simply, if I want, I will be extreme in drawing. If the bar is having this shape, when we apply force to it, with applying force is going to have something like this. So when you look at this side, for example, it's longer. It's going to be longer as compared to the original position. So the change in the length, you can say, is what is known as the strain. So the strain by definition is given here as the change in L, delta L over the original length. That's how. So let us here make use of this idea, the deformation. To make use of it, we are going to put the strain gauge on the surface of that bar. So if the length of the bar change, that's going to cause torsion to the piece, the sensitive piece. If we make that kind of torsion, it's going to change its resistance. So that's how we are going to convert the force applied to resistance. That's mainly the idea. Of course, this piece, which the sensitive piece, will be placed on this bar, which made of material special for that. Now, gauge factor is important element or important properties help us to calculate the strain or calculate the resistance. What is the gauge factor? Gauge factor, which known as a K, it's given as the change in delta R, the change in R over R, the change in the resistance R divided by R divided by the change of L divided by L. What do you mean by that? Of course, this material is having this certain resistance. That resistance, when there is no strain applied, it's, for example, R. No strain applied. When I apply strain, when I apply force to the material, the value of the resistance here will change. Will it change by delta R? Let's say it's R. Now it's R plus delta R after we apply the force. So when I divide this delta R divided by R, I'm going to get this part. Same thing, before we apply the force, there will be a length. After we apply the force, there will be change in the length. This is the change in the length. So the change in the length over the length is going to make this factor, this factor here. Now, the delta R over R divided by epsilon is known as the gauge factor. Epsilon is known as the strain, which delta L over L. Okay, that's the idea of strain, or sorry, the gauge factor, or from there we can calculate the strain and we make relation between resistance and the strain. Let us consider this example on the strain gauge, which will help us to understand the relation between the resistance and the strain. So the example is saying certain material being measured under stress undergoes a strain of 5 parts per million, means 5 micro epsilon. That's the strain. So the strain is 5 micro epsilon. Okay, the strain gauge has a normal unstrained resistance of 320 ohm. That means before the strain, before we apply the force, or before the strain, its resistance is 320 ohm. The gauge factor K equal to 2. Determine the following. We need to calculate here the resistance, the resistance change in the strain gauge. Remember that the resistance was 320. What is the change in the resistance? So we go to calculate it using this formula. So the gauge is known to us. The gain constant, which the gain it's what to say, strain gauge constant is K, is known to us. We have delta R is needed, R is known, delta L over L is given. So I can say, if I want to write it in different way for easy dealing with the values, I can say K equal to 2, which equal to delta R is needed over R is 320 divided by delta L is delta L over L is epsilon. Delta L over L is epsilon. So it's given as 5 part per million. That means 5 into 10 to the power minus 6. So if you notice, we have one equation with one unknown, delta R. You can rearrange the equation to get this, and you will find that delta R equal to 3.2 milli ohm. Okay, now the new resistance of the strain gauge, the new resistance is equal to the old resistance plus the change in the resistance, because before strain it was 320 and there is a delta of 3.2 milli. The new resistance will be the unstrained resistance plus delta L 320 plus 3.2 into 10 to the power minus 3, which equal to this value. Another example here, resistance strain gauge with a gauge factor of 2 is cemented to a steel member with which subjected to a strain of 10 to the power minus 6. If the original resistance is 130 ohm, the original resistance is 130 ohm, calculate the change in the resistance. Very simple, we can use the equation, the same equation, and we know that K equal to 2, which equal to, same as before, delta R over, what is R? It's 130 divided by delta L over L is equal to 1 into 10 to the power minus 6. So we will calculate it to get delta R. If you want the resistance after the strain, we can add it to this value. That's all about the strain gauge. I hope everything is clear. Thank you very much.